Okay, so for anyone out there really pushing the limits of what LLMs can do, better than anyone, they can kind of hit a wall when it comes to really complex reasoning.
Yeah.
Especially when you need them to use like external knowledge sources and figure things out that are beyond just the data they were trained on.
Right.
That's what we're going to dive into today.
Yeah, absolutely.
This is a really interesting paper. It's called Learning to Reason with Search for LLMs via Reinforcement Learning.
Catchy title.
Yeah, very catchy. Also, sometimes called ReSearch for short. And it's from a whole team of folks over at Baiswan Inc. and a few different universities.
I think a lot of the authors are from Baiswan Inc., but there's also Tongji University.
Oh, right.
The University of Edinburgh's is JAME University. So yeah, quite the collaboration.
Yeah, a real powerhouse team. And the core idea that they're tackling is how to train these LLMs, think like your Qwen 2.5 models and so on, to use web search in a much smarter way as part of how they reason things out. And the really cool part is they're doing this with reinforcement learning.
Yeah.
And they don't need like a ton of labeled data to show the LLM how to think step by step.
Exactly.
So it's kind of like, you've probably heard of Retrieval-Augmented Generation, RAG.
Right.
Everyone's talking about RAG these days.
It's all the rage.
But this is like taking RAG to the next level instead of just retrieving documents and reading them.
Yeah.
It's like actually reasoning with search. Like it's a core part of thinking.
Right. Like it's one of the tools in the toolbox that it can use.
Exactly. Yeah. And what they're finding is this not only helps with those really tricky multi-hop questions where you need to connect information from different places.
Like you have to go through multiple steps to get to the right answer.
Right. Yeah. But it also seems to generalize pretty well.
Which is huge.
Yeah. That's the really exciting part because, they train this on just one data set.
Really?
And it's doing well across the board.
That's super impressive.
Yeah. So that's what we want to unpack today. How does research actually pull this off?
Yeah.
We'll get into the nitty-gritty of their reinforcement learning method.
Just love it.
Look at the results they got and what this all means.
Okay.
For, the future of building like truly smart AI systems.
That's good to me.
So this is like, right at the bleeding edge of AI research.
Yeah. I mean, if you're trying to stay ahead of the curve, this is the kind of stuff you got to be paying attention to.
Absolutely. So let's jump right into the core challenge here.
Okay.
We both work with ARG a lot.
Every day.
And we know that standard ARG methods kind of struggle when you throw really complex real-world problems at them.
Totally. I mean, like, take a question that needs information from a bunch of different sources. Like, that's where things start to break down.
Right. It's like a multi-stage puzzle.
Yeah.
But you only get the first clue.
Exactly. And classic ARG is just kind of hoping for the best.
Right. Grab a few documents up front and that's it.
Yeah. It's like, here you go. Figure it out.
Exactly. Yeah. But in the real world, you need to be able to kind of like, figure out what information is missing and then go and find it.
And then search for that specifically. And that's the gap that research is trying to fill.
Okay. So what are some of the, specific issues?
Okay. So one big problem is that a lot of these existing multi-step RE methods, they rely on these like really carefully crafted prompts.
Yeah.
Or they have like a fixed strategy that's like pre-programmed. Which is super brittle.
Right. It's like, writing a script for every possible conversation.
Yeah, it just doesn't scale. And it's definitely not going to work for anything new or unexpected.
Exactly. And the other thing is like, imagine trying to actually label all the intermediate reasoning steps.
Oh my gosh.
In this multi-step RE process.
Yeah.
What's the correct thought at each stage?
Right. Is this the right search query? Should I be looking for something else? Like, it gets really messy.
It's totally subjective and just, you can't scale that.
Not a chance.
So that's where research comes in.
Okay, hit me with it.
What's the big idea here that they're doing differently?
Okay, so the magic of research is that they bake these search operations right into the LLM's thinking process.
Okay.
They have these special tags like search and search to tell the LLM, hey, this is where you should be searching and this is what you should be searching for.
Okay.
And then they use result and result to kind of package up the information that comes back from the search engine.
Yeah.
And the key is that these aren't just like afterthoughts.
Right.
These tags are like fundamental parts of the reasoning process itself.
So it's not just retrieve and then reason.
It's not just tacked on at the end.
The reasoning is actually guiding the retrieval.
It's all interwoven.
Wow. Okay, so the LLM is thinking about things.
Yeah.
And then it realizes, oh, I need more information.
Exactly.
Let me formulate a search query.
And then, boom, it sends that query off to the search engine.
And then it gets the results back and uses that to keep thinking.
It's this beautiful back and forth.
Like a real researcher.
Right. A human would do the same thing.
Exactly. You form a hypothesis, you go look for evidence.
And then you adjust your thinking based on what you find.
And then repeat.
Rinse and repeat.
So to get this to work without like hand-holding the LLM every step of the way, they use reinforcement learning.
Of course.
Right? Everybody's doing reinforcement learning these days.
It's eating the world.
But tell us a little bit of the specific method they use.
So they call it GRPO.
GRPO.
Which stands for Group Relative Policy Optimization.
Group Relative Policy Optimization.
Yeah, it's a mouthful.
It is a mouthful.
But the basic idea is that you train the LLM by rewarding it for generating these sequences of thinking and searching.
Okay.
They call these rollouts.
Rollouts.
That lead to the right answer.
Okay, so it's like trial and error.
Pretty much the model is constantly experimenting with different paths.
And if it stumbles on the right answer,
bingo,
it gets a little pat on the back.
It gets a reward, and then it's more likely to try that again in the future.
Okay, so now GRPO is a little bit different from some other reinforcement learning methods out there.
Yeah, like PPO.
Right, Proximal Policy Optimization.
Yeah, a lot of people use that one.
But with GRPO, they don't use a separate critic model to tell them how good each action is.
They ditch the critic.
Instead, they estimate a baseline from a bunch of different rollouts.
Exactly. So for each question, the model generates a bunch of different attempts.
Okay.
And then GRPO looks at the rewards from all of those attempts to figure out which ones were better.
Like internal competition.
Yeah, it's like the model is competing against itself.
And learning from its own mistakes.
Exactly.
Cool. So this objective function that you mentioned, what's it actually trying to do?
So basically, it wants to increase the probability of those better performing rollouts.
Okay.
Like the ones that got higher rewards.
Uh-huh.
And it does this by comparing the new policy, which is like the updated LLM, to the old policy.
Okay.
And they use this ratio to make sure the updates aren't too drastic.
Right. You don't want to completely change the LLM's personality.
Exactly. You want it to learn, but you don't want to break it.
Yeah.
They also use this thing called a KL Divergence Penalty.
Oh, yeah.
Which basically prevents the new policy from straying too far from the original LLM.
Keeps it grounded.
Yeah, like an anchor.
Okay, so let's walk through this rollout with search process step by step.
Okay.
Like what's actually happening as the model tries to answer a question.
All right, so it starts off with the LLM doing some thinking, just good old-fashioned natural language processing.
In its own little brain.
Yeah, exactly. And that's all inside those think tags. But then at some point, the LLM might be like, I need more information here.
Okay.
And that's when it generates a search query, which it puts inside those search tags. And when it hits that closing search tag, that's the signal to send that query off to the search engine.
Like it hits enter.
Yeah, exactly. And in this case, they're using a system built on FlashRag with the E5 base V2 retriever, which is searching through a snapshot of Wikipedia from December 2018.
Okay.
And it brings back the top 5 most relevant results.
Top 5.
Yeah, and those get injected back into the sequence, wrapped up in those result tags.
And then the LLM gets to see all of that.
The whole thing, the initial thoughts, the search query, the result.
The whole shebang.
Yeah, and it uses all of that to keep reasoning.
And this whole cycle can repeat.
Oh, yeah. As many times as needed.
So it could think a little bit search, think a little bit search again?
Exactly, until it gets to the answer or hits the end of the sentence.
And hopefully the answer is wrapped up in those answer tags.
Nicely formatted with the boxed around it.
Yeah, so this retrieval result masking thing.
Yeah, that's a good one.
This seems really important.
It's subtle, but it's super important.
Why is it so crucial during the loss calculation?
Okay, so remember, in reinforcement learning, the reward is used to update the LLM based on what it generates.
Yeah.
But those result tags, that's information that came from outside.
Or the search engine.
Right, the LLM didn't generate that.
Yeah.
So if they didn't do anything special, the LLM might just learn to copy and paste from the search results.
Oh, I see.
Like, why bother thinking if I can just spit out whatever Wikipedia says?
Right, be lazy.
Exactly. So they mask out those result tokens during training.
Oh,
so the model doesn't get credit for them.
It's only rewarded for the things that it actually came up with.
Right, the thinking steps and the search queries.
Like we said, you want to teach it how to fish.
Not just give it a fish.
Exactly. All right, so let's get into the experiment itself.
Okay.
What kind of LLMs did they actually use for this?
So they went with the Quen 2.5 models.
Qwen 2.5, okay.
Yeah, the 7B and 32B versions.
So a smaller one and a larger one.
Yeah, just to see how they compare.
Uh-huh.
And they use both the base models and the instruction-tuned versions.
Interesting, okay.
And get this, they only train on one data set.
One data set.
Just music.
Music, okay, I've heard of that.
Yeah, it's designed for multi-hop question answering.
Right, so it forces the model to think in multiple steps.
Exactly, and to use information from different places.
Okay, so perfect for testing out this idea.
And they only trained for 2 epochs.
2 epochs, is that all?
Yeah, which is pretty remarkable.
So for the external knowledge source, you said they used FlashRag?
Yeah, FlashRag with the E5 base V2 retriever.
Okay.
And they were searching Wikipedia from December 2018.
Okay, so a fixed snapshot of Wikipedia.
Yeah, and they always retrieve the top 5 results.
Got it. So 2 epochs on a single data set.
You got it.
And they saw actual improvements.
That's the crazy part.
That's really impressive. And what about the prompts? Were there any like crazy prompt engineering tricks?
No, they kept it pretty simple.
Okay.
Actually, they took inspiration from DeepSeek R1, which is known for its straightforward prompts.
Mm-hmm.
They used 2 different templates, though.
Okay.
One for the base models and one for the instruction-tuned models.
Okay, so slightly different depending on the starting point.
Exactly. For the base models, the question itself was the input.
Okay.
But for the instruction-tuned models, they used the template as the system prompt.
Okay, so kind of setting the stage.
Yeah, like giving it a little guidance.
And both templates made it very clear how to use those tags.
Yeah. Think, search, result, answer.
So the LLM knew exactly what was expected of it.
No confusion.
Okay. So how did they measure whether the model was actually learning?
Yeah, what was their reward function like?
Right.
So they kept the reward function pretty elegant, too.
Okay.
It has 2 parts, an answer reward and a format reward.
Answer reward and format reward.
Yeah. The answer reward is based on the F1 score. Between the model's final answer and the true answer.
Right.
So how close did it get?
Yeah.
And the format reward is just checking that it used the tags correctly.
Okay.
And that the final answer is in that boxed format.
So it's not enough to just get the right answer.
It has to present it nicely.
You got to follow the rules.
Exactly. And they gave specific rewards based on these criteria. Okay.
So if the F1 score was greater than 0, the reward was just the F1 score itself.
Okay.
But if the F1 score was 0, but the format was correct, they still gave it a small reward, like 0.1.
It's a little encouragement.
Yeah, like, you're on the right track, keep trying.
And if both were wrong...
Then it got nothing. 0 reward.
Tough love.
You got to learn somehow.
So let's get to the result.
Everyone's favorite part.
How did ReSearch actually perform compared to those baseline methods?
So across the board, ReSearch was significantly better.
Okay.
They tested it on 4 different data sets: Hotpot QA, 2Wiki multi-hop QA, Music, which is the one they trained on,
Right.
and Bamboogle.
Okay.
And they compared it against a bunch of different baselines.
Like what kind of baselines?
So they had a naive generation approach where the model didn't use RGAI at all.
Okay, so just straight up generation.
Yeah, and then a basic ROG implementation where they just stuck the retrieved documents onto the question.
Like a very simple version of RGAG. Exactly, and then they also compared against 2 more sophisticated multi-step RAG techniques, Idirection and IRK.
Okay, so these were like the state of the art.
Yeah, the best of the best.
And ReSearch beat them all.
It did, and by a decent margin.
Like how much better are we talking?
So for the 7B model, ReSearch got about a 15.8% improvement in exact match accuracy.
Wow, okay.
And about 17.6% when they used GPT-4 Mini as a judge.
Okay, so a large language model to assess the answers.
Yeah, and the 32B model was similar.
So consistent improvements across the board.
Yeah, across different model sizes and different data sets.
And remember, this was all trained on just music.
Just one data set.
So it's generalizing really well.
That's the amazing part.
That's huge.
And they also found that starting from an instruction-tuned model was better than starting from the base model.
So you get even more bang for your buck.
Exactly.
Yeah.
The instruction-tuned models just had a head start.
They were already primed for this kind of task.
It's like they already knew how to follow instructions. So it was easier for them to learn this more complex reasoning with the search behavior.
Okay, so you're saying if I'm going to use ReSearch, start with an instruction-tuned model.
Definitely.
Okay, now they also looked at like the training dynamics?
Yeah, they wanted to see how the model was learning over time.
Right, like what was it actually doing?
So they track things like the length of the generated responses and how often it was searching.
Okay, so what did they find?
So generally, they saw that the responses were getting longer as training went on.
Longer responses, okay.
Yeah, especially for the instruction-tuned models.
Yep.
But there was this interesting thing with the 32B base model.
Yeah.
It actually got shorter at first.
Oh, weird.
And then it started getting longer.
Okay, so what's going on there?
So they think maybe the bigger model was trying to rely on its own knowledge at first.
Okay.
Like it was trying to answer everything from memory.
And then it realized it needed help.
Yeah, it realized that search was actually a useful tool.
So it started searching more and the responses got longer.
Exactly.
Makes sense. And what about the number of searches?
So that was consistently going up throughout training.
Okay.
Which means the model was learning to use iterative search.
Iterative search. Okay.
Like doing multiple searches in a row.
Right, not just one and done.
Yeah, it was really embracing that multi-step approach.
Okay.
Which is exactly what they wanted.
Cool. And what about those reward curves?
So the reward curves were pretty typical. They shot up at the beginning and then slowly improved.
Like it was figuring things out quickly.
Yeah, and then fine-tuning its strategy.
And the instruction-tuned models started off higher.
Yeah, they had that advantage.
And for the 7B models, the base and instruction-tuned versions ended up with pretty similar rewards.
Yeah, but for the 32B models, the instruction-tuned one got a higher final reward.
Okay, so bigger model plus instruction tuning.
Yeah, that's the winning combo.
All right, so the paper has this really cool case study.
Yeah, this is a great example.
Walk us through it.
Okay, so the question is, who won the 2018 presidential election in the country where the political party of Martin Ramirez Peck operates?
Okay, kind of a complex question.
Yeah, it's not a simple one-step answer.
Right.
So the model starts off thinking it needs to figure out which country this guy's political party is in.
Okay, makes sense.
So it searches for Martin Ramirez Peck.
Right.
But the first result is about a different person, also named Martin Ramirez.
Oh, okay, so wrong guy.
Wrong guy.
Classic search engine problem.
Right, and here's the amazing part in the next think step.
Yeah.
The model actually says, it appells that I made a mistake in my search query.
No way.
Yeah, it recognizes its own error.
That's so cool.
And then it corrects itself.
Wow.
It generates a new query, Martin Ramirez Peck political party.
Okay, much more specific.
Exactly, and that leads it to results about the Labor Party in Mexico. So now it knows the country. So it searches for 2018 Mexican presidential election.
And that gives it the answer.
Bingo Andres Manuel López Obrador.
And presents it nicely in the answer tags.
Perfectly formatted.
So it not only figured out the answer,
yeah,
but it also recognized its own mistake and fixed it.
Like it was thinking critically about the search results.
That's amazing. And they didn't explicitly program it to do that.
Right. That just emerged from the reinforcement learning.
It's like it learned to be a better researcher.
Yeah. It's like it developed this self-reflection ability.
That's incredible.
It's really exciting.
So for all those AI researchers and ML engineers listening,
yeah,
what are the key takeaways from this paper?
Okay, so the main thing is that research is a really clever way to train LLMs to reason with search. And it does it without needing labeled data for the reasoning steps.
Right, which is a huge time saver.
Yeah, and by treating search as part of the reasoning process itself and using this GRPO algorithm, they got some really impressive performance improvements on these multi-hop question answering tasks.
Okay.
And the fact that it generalizes to other data sets, even though it was only trained on one, shows that it's a pretty robust approach.
Yeah, that's really encouraging.
And then you've got these emergent behaviors like self-reflection.
Right.
Which is just amazing.
That's the really mind-blowing part.
It is.
So why should our listeners care about research?
Okay, so if you're building LLMs for real-world applications, research is a big step towards making them more capable and more reliable.
Oh.
Because you don't have to spend all this time crafting prompts or labeling data.
Yeah.
It can just learn how to use external knowledge on its own.
And that means we can build systems that are more accurate.
Yeah.
More trustworthy.
More reliable.
And just more capable overall.
Exactly.
So any final thoughts for our technically minded audience?
So research showed us that we can integrate web search into an LLM's reasoning process.
Yeah.
Using reinforcement learning. But what if we could go further?
Okay, I like where this is going.
What if we could integrate other tools?
Like what kind of tool?
Like code interpreters or math solvers or even robotic systems.
Wow.
could we use reinforcement learning to teach LLMs how to use all these tools?
As part of their thinking.
Yeah, seamlessly integrated into their reasoning.
That would be incredible.
It would be a game changer.
But also probably very challenging.
Oh, yeah, definitely. We'd have to think about safety.
Right.
Controllability.
Yeah.
Interpretability.
A whole new set of challenges.
But the potential is huge.
It is.
Yeah.
So for everyone listening, if you want to dig deeper into research, the link to the paper is in the show notes.
Check it out.
It's a fascinating read.
It really is.
Thanks for joining us for another deep dive.
My pleasure.
And we'll see you next time.
See you then.